Hello class, today we'll be going over Fischer esterification. Now esters are quite prevalent in our society. They're quite useful. So they're used from food such as artificial sweeteners, even to clothes. I'm sure you've heard of polyester. As well, they tend to have a strong odor, so they can often smell like bananas or cinnamon or lemon. And with the experiment that we'll be doing, we're forming isopentyl acetate, which has the smell of bananas. As well, a meal Fischer, for which this process is named after, is also the namesake of Fischer projections, which I'm sure you've heard of in Organic 1 or 2, as well as he's considered laying the foundation for biochemistry, especially with his work with carbohydrates and elucidating their structures. Now we'll be going over esterification, which requires an acid catalyst. Acidic conditions, but all these processes, all these steps are reversible. So this reversing of it, especially in basic conditions, is considered saponification. So let's see, where do we begin here? So first we have our carboxylic acid, and we are protonating the carbonyl oxygen of the carboxylic acid with our acid catalyst, forming an oxygen with has 3 bonds to a triple bonded oxygen. So this will have a positive charge, which will strongly pull the electrons from the carbonyl carbon towards itself. So the electron density of the carbonyl carbon decreases, which increases its electrophilicity, or the nucleophile's attraction to it. So we have our nucleophile here, which will be our alcohol, which will also act as our solvent in many labs, including ours. So with that, we have our oxygen from our alcohol attacking our carbonyl carbon, and here we are forming our tetrahedral complex. So this is also considered the rate determining step. So the speed at which this step is able to occur will have a very strong effect on the overall reaction time. So here we have another triple bonded oxygen, where our alcohol is connecting to the carbonyl carbon, or what was the carbonyl carbon. So it has a positive charge. It wouldn't mind giving up a proton to form just 2 bonds, to which oxygen prefers. So another of our solvent molecules, our alcohol, will do the job of just removing this proton off of the alcohol, of the alcohol, forming an ether. So here we have 2 hydroxyl groups. Both of them are able to pull off a proton from another one of our solvent molecules, maybe even the one we just formed, or the one that was just protonated. And now creating a water molecule. So with that, we have the other alcohol molecule is its electron pair, one of them, can reform the double bond, pushing off the water molecule. And as you know, water molecules are very good leaving groups. So that's just going to get out of there. So now here we have another triple bonded oxygen with positive charge. I wouldn't mind giving up a proton. So here we have one more of our solvent molecules, removing the proton from this carbonyl oxygen. As well, since we have just formed water, it's possible for a water molecule to perform the same job, but right now I'm just drew out another alcohol molecule. And with that, we have our final product, our final 2 products. We have both water, because this is a condensation step right here, as well as our final ester product. So it's also possible for this esterification to occur in the same molecule, an intramolecular esterification. So here, especially the product is especially favored if it's forming a stable 5 or 6 membered ring. so forming our cyclic ether with very much the same process, acid catalyst. So our main reaction that we'll be going over is with isopentyl alcohol and acetic acid. So with acetic acid being the main molecule, or the main chemical in vinegar. So we'll also be using sulfuric acid, just only a few drops, to form our isopentyl acetate, our banana oil. So back to the rate determining step. So with this rate determining step, with the nucleophile attacking the carbonyl carbon and attaching itself, the more electrophilic you can make this carbonyl carbon, the faster this reaction will proceed, or the more easily this nucleophile can attack, then the quicker this reaction will proceed. So it can be influenced by both steric effects and electronic effects of the substituent. So, as you know, the more sterically hindered the carbonyl carbon is, the less likely it is for the nucleophile to attack it. So if you have a big substituent on the alpha or the beta carbon of the carbonyl group, then it's going to be very hard for the nucleophile to get to the carbonyl carbon to attach. So the smaller the substituent is, or the substituent on the alpha or a beta carbon, if it has one, then the quicker this overall reaction will proceed. As well, just as this oxygen here having a positive charge affected the electrophilicity of this carbonyl carbon, it's the same. The same can be said for the substituent. So the substituent can either be electron donating or electron withdrawing, rather strong or weak in either direction. So electron withdrawing groups, such as chlorine or chlorine molecule or bromine molecule, it will pull electron density off of this carbon, making it more prone to a nucleophilic attack. Whereas if we had an electron donating substituent, this reaction would proceed overall much slower because it's donating some electron density. So it's not quite as prone to the nucleophilic attack. And finally, I'll leave you with a quick tip just for if you're having trouble visualizing the product of a Fischer esterification process. So you just take out you draw out your carboxylic acid with the hydroxyl group over here on one edge, or over here on one end, and draw your alcohol here on the other end with the acidic proton of the alcohol facing the carboxylic acid, the hydroxyl group. And overall, you're just going to eliminate a water molecule and replace this oxygen here with the oxygen and the alcohol's alkyl group, forming your final product here. As you can see, drawn out here, we have our oxygen. Oh, oops! It appears I didn't draw it out quite as I thought, but still. Overall, that just is able to help you visualize it more easily. So if you have any future problems, it's you're more able to get to the solution faster. Well, I hope you have a great time in lab, and I'll see you there.